STP is designed to prevent looping in Layer 2 networks caused by broadcast traffic and physical loops. It was standardized in 802.1d and is now included in 802.1q. In a Layer 3 network, routers by default do not forward broadcast traffic between their interfaces. They utilize routing protocol loop prevention mechanisms and the time to live (TTL) field in the IP header to prevent traffic looping at Layer 3. However, switches behave differently when they receive broadcast traffic. They forward the broadcast frames out of all ports, except the one they were received on. This behavior can lead to broadcast storms if a physical loop exists in the Layer 2 network. Unlike in Layer 3 headers, there is no TTL value in Layer 2 headers. Therefore, if a loop exists, broadcast frames will continuously circulate within the loop, consuming switch CPU and bandwidth and rendering the network unusable. To prevent broadcast storms and loop-related issues, Spanning Tree Protocol, STP, was introduced. STP and its variants exchange Bridge Protocol Data Units, BPDUs, between switches to detect loops and take necessary actions to close them. This usually involves blocking specific switch ports to eliminate loops. Although blocking ports reduces the number of active paths and available bandwidth in the network, it is necessary to maintain network stability. STP defines two permanent states for ports. Forwarding. In this state, ports send and receive frames as normal. Blocking. Discarding in RSTP. Ports in this state do not send or receive any frames except for receiving BPDUs. This prevents the forwarding of frames that could potentially cause loops. Additionally, there are two transient states in classic STP. Listening. This state is not present in RSTP. In the listening state, ports do not forward frames but listen to incoming frames to remove stale MAC entries that might cause loops. Learning. In this state, ports do not forward frames but listen to incoming frames to learn MAC addresses. This helps switches build their MAC address tables. When switch ports initially come online, they are in the blocking state. If there are no loops detected, the ports transition to the forwarding state. Ports that are administratively disabled or have failed are considered to be in a disabled state, meaning they are non-operational. Overall, STP plays a crucial role in preventing broadcast storms and maintaining network stability by detecting and eliminating loops in Layer 2 networks. The Spanning Tree Process. The Spanning Tree Process involves the election of a root bridge and the configuration of all switches to ensure a loop-free network topology. Here are the key details. Root bridge election. During the Spanning Tree process, a root bridge is elected. The root bridge is the central switch in the network that serves as the reference point for all other switches. By default, Spanning Tree is enabled on switches, and they automatically go through the process of electing a root bridge and blocking redundant paths. It is recommended to manually select the root bridge as a higher performance switch located centrally in the network, rather than relying on the automatic election process. Bridge ID, BD, and root bridge selection. Each switch participating in the Spanning Tree process sends Bridge Protocol Data Units, BPDUs, containing its bridge ID, BID. The BID consists of an 8-byte identifier that uniquely identifies the switch on the LAN. It includes a 2-byte bridge priority field, which can be configured, and a 6-byte system ID based on the switch's MAC address. The bridge priority can range from 0 to 65535, with 32768 being the default value. The switch with the lowest bridge priority becomes the root bridge. In case of a tie in bridge priority, the switch with the lowest MAC address is selected as the root bridge. BPDUs and hello messages. When switches start up, they send BPDUs with their own bids as the root. As they receive BPDUs with better bids, they start announcing the new root bid. Each switch also sends hello BPDUs at regular intervals. The hello BPDU contains information such as the root bridge ID, sender bridge ID, sender root cost, the cost of the path from the sender to the root, and timer values. Timer values, including hello intervals, max age, and forwarding delay, are set by the root bridge and adopted and forwarded by other switches. Hello interval, the time interval between hello messages, which defaults to 2 seconds. Max age, the duration. A switch should wait when it does not receive hello BPDUs before attempting to change the network topology. It defaults to 10 times the hello interval, 20 seconds. Forwarding delay. The time a switch should stay in each transient state, listening and learning, when changing the network topology. It defaults to 15 seconds for each state. The spanning tree process ensures that switches converge on the best route bid over time, allowing for a stable and loop-free network topology. In the example below, the bridge priority has not been manually set on any switches. CD1 is elected as the root bridge because it has the lowest MAC address. The other switches detect their lowest cost path to the root bridge. Higher bandwidth links are preferred by default, but port priority can be manually set. These paths transition to a forwarding state. Each switch's exit interface on the lowest cost path to the root bridge is selected as its root port. A spanning tree instance does not do load balancing. If a switch has multiple equal cost paths towards the root bridge, it will select the neighbor switch with the lowest bridge ID. In the example below, AC3 selects the path to the core 1 root bridge via DIS2 as it has a lower bridge ID. It does not also select the link to DIS1 as that would potentially form a loop. In the example below, ACC3 selects the path to the core 1 root bridge via the left-hand link to DIS2 as it is the port with the lowest port ID going to the lowest bridge ID. It does not also select any of the other 3 links, as that would potentially form a loop back to itself from the upstream switch. Ports on the neighbor switch opposite the root port are designated ports. Root ports point towards the root bridge. Designated ports point away from it. All ports on the root bridge are always designated ports. Root ports and designated ports are the most direct paths to and from the root bridge and transition to a forwarding state. On the remaining links, the switches determine which of them has the least cost path to the root. If they have equal cost paths, then the bridge ID is used as a tiebreaker. The port connecting this switch to the link is selected as a designated port. Any ports which have not been selected as a root port or designated port pair would potentially form a loop. These are selected as blocking ports. Spanning tree only blocks ports on one side of the blocked link. BPDUs continue to be sent over the link, but other traffic is dropped. The easy way to figure out which ports are root, designated and blocking. 1. Determine the root bridge first, best bridge ID. 2. All ports on the root bridge are designated ports. 3. Determine the root ports on the other switches, lowest cost to root bridge. 4. The ports on the other side of those links are designated ports. 5. On the links which are left, one port will be blocking. 6. Determine the blocking port, highest cost path to root bridge or highest bridge ID. 7. The ports on the other side of those links are designated ports. Convergence, the process by which switches react to changes in topology and agree on how to change how frames are forwarded, happens when a switch stops receiving hello BPDUs on its root port for a period determined by Maxage timer or when the link on root port fails. Rapid Spanning Tree Protocol, RSTP, is a protocol used in computer networks to prevent loops and ensure efficient communication. It was introduced in 1998 and standardized in 2001 as an amendment, 802.1W, to the 802.1D standard. RSTP has undergone revisions and is now included in the 802.1Q standard. RSTP shares several similarities with the classic Spanning Tree Protocol, STP, including the election of a root bridge, the selection of a root port, the election of a designated port, and the presence of forwarding and blocking states. However, RSTP introduces several improvements to enhance convergence speed and efficiency. Here are the key differences and improvements provided by RSTP. 1. Quick replacement of ports. In RSTP, an alternate port can quickly replace a root port without waiting for the port to enter a forwarding state. Similarly, a backup port can quickly replace a designated port without waiting for the port to enter a forwarding state. This allows for faster convergence when there are changes in the network topology. 2. Shortened timers. RSTP reduces the Maxage timer to 3 times the hello timer, typically resulting in a 6-second interval. This change accelerates the detection of topology changes and speeds up the convergence process. 3. Rapid link failure detection. RSTP introduces a mechanism where a switch can ask its neighboring switch about a possible link failure instead of waiting for the Maxage timer to expire. This mechanism enables quicker detection and recovery from link failures. 4. Hello BPDUs generated by each switch. Unlike STP, where Hello Bridge Protocol Data Units, BPDUs, are generated only by the root bridge, RSTP requires each switch to generate Hello BPDUs. This ensures that all switches in the network have the same timer settings and improves communication and synchronization. 5. Discarding state. RSTP combines the STP blocking and disabled states into a single discarding state. This simplifies the state transitions and reduces the convergence time. 6. Elimination of listening state. RSTP removes the listening state present in STP. Instead, it jumps directly from the discarding state to the learning state, further reducing the convergence time. When a switch detects a topology change and needs to replace its root port, the following steps occur in RSTP. 1. The switch informs the switch connected to its alternate port that a topology change has occurred and requests it to flush relevant entries in the MAC table to avoid loops. 2. The switch flushes relevant entries in its own MAC table to avoid loops. 3. The switch designates its alternate port as the new root port and moves it into the forwarding state. 4. The old root port is moved into the discarding state. 5. A new alternate port is selected. This process bypasses the listening and learning states, which were present in STP but are not utilized in RSTP. RSTP introduces different port link types to optimize the convergence process based on the characteristics of the links. These link types determine how RSTP behaves when converging on specific types of connections. Here are the main RSTP port link types. 1. Point-to-point. This link type refers to a full duplex link between two switches. By default, if the port-fast feature is disabled, this link type is assumed. Convergence on point-to-point links requires entering the learning state. 2. Point-to-point edge. This link type represents a full duplex link between a switch and a single-edge device, such as a PC. Since the switch doesn't have information about what is connected on the other side, this link type is typically set when port-fast is enabled on a port. Ports on point-to-point edge links bypass the learning state during convergence, allowing for faster convergence. 3. Shared. The shared link type assumes half-duplex links connected to a hub. Convergence on shared links is slower compared to point-to-point links due to the nature of half-duplex communication. In addition to the port link types, RSTP also supports the concept of Ether channel. Ether channel allows bundling multiple Layer 2 or Layer 3 links up to 8 together into a single logical link. This bundling provides load balancing and quick failover in case of link failures, improving performance and resilience in the network. RSTP also includes a feature called BPDU Guard, which helps prevent certain network issues. BPDU Guard, when enabled on a port, disables the port if it receives a Bridge Protocol Data Unit, BPDU. This feature is used to prevent rogue switch attacks, where an attacker becomes a root switch to eavesdrop on network traffic, as well as incidents caused by non-STP/RSTP aware switches being connected and causing loops in the network. To configure BPDU Guard, the following commands can be used. Enable BDPU Guard on all access ports by default. Spanning tree BPDU Guard default enables BPDU Guard on all access links by default. No spanning tree BPDU Guard default disables BPDU Guard on all access links by default. Enable or disable BDPU Guard on a specific interface. Spanning tree BPDU Guard enables BPDU Guard on the specified interface. Spanning tree BPDU Guard disables BPDU Guard on the specified interface. If an interface with BPDU Guard enabled receives a BPDU, it will be automatically disabled to protect the network. To manually restore the interface, the shutdown and no shutdown commands can be used. For automatic recovery, the following commands can be used to configure the interval before the interface is automatically recovered from an error, including BPDU Guard. Error-diceable recovery cause, BPDU Guard, enables automatic recovery from BPDU Guard errors. Error-diceable recovery interval seconds sets the interval in seconds before automatic recovery occurs. It's important to note that the automatic recovery configuration applies to all types of errors, not just BPDU Guard. Overall, these port link types and features in RSTP help optimize network convergence, enhance security, and improve the efficiency of communication in a switched network environment. Port-fast is a feature in RSTP that allows an interface to transition directly from the blocking state to the forwarding state without going through the listening and learning states. This feature is designed for ports connected to end devices, such as PCs or servers, as they do not participate in the spanning tree protocol and cannot create loops in the network. Enabling port-fast on these ports helps to reduce the time it takes for the end devices to access the network immediately after being connected. To configure port-fast, the following commands can be used. Enable or disable port-fast on a specific interface. Spanning tree port-fast Enables port fast on a specific interface. Note that the interface must be an access port. Spanning tree port fast disable. Disables port fast on a specific interface. Enable or disable port fast on all access links by default. Spanning tree port fast default. Enables port fast on all access links by default. No spanning tree port fast default. Disables port fast on all access links by default. It's important to note that port fast should not be enabled on ports that are connected to other switches to prevent the creation of loops. Additionally, when enabling port fast on a port, it is recommended to also configure BPDU guard to ensure that the port does not receive BPDU packets from other switches, which could potentially cause loops. Root guard is another feature in RSTP that prevents a device connected to a specific port from becoming the root switch. This feature is useful when the network administrator manually sets the root bridge near the center of the network and wants to ensure that any new switches added to the network do not take over the root role. Enabling root guard on a port helps to maintain the stability and control of the network topology. Loop guard is used to prevent loops that may arise from connectivity failures, such as a unidirectional link where frames can only travel in one direction due to a broken wire inside the cable. Loop guard is incompatible with root guard and will be automatically disabled if root guard is enabled on a port. To configure root guard and loop guard, the following commands can be used. Enable or disable root guard or loop guard on a specific interface. Spanning tree guard root enables root guard on a specific port. Spanning tree guard loop enables loop guard on a specific port. Spanning tree guard none disables root guard and loop guard on a specific port. Enable loop guard on all interfaces by default. Spanning tree loop guard default enables loop guard on all interfaces by default. These features in RSTP, such as port fast, root guard and loop guard, provide additional control and protection mechanisms to prevent loops, ensure stable network operation, and maintain the desired network topology. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.